Here's the notes for the second portion of chapter 1.4. We're going to do linear regressions today. This shouldn't be anything super new to you. You should have done it in Algebra 1 for sure if you didn't get it in Algebra 2. The first step is that if you haven't yet, so if your class didn't get to this, make sure you copy this down. So go ahead and pause the video and copy this down right now. Okay. Once we have that, this is what you're going to do in the calculator. These are the calculator steps. So I'm going to have you follow along with me. You need to take notes. That's required. You must be watching this video on Edpuzzle. If you are not watching it on Edpuzzle, you will not get credit for this video. Make sure you have your calculator out and ready, either with you or on the computer. I'm about to use the one on the computer. So the first thing, it says to turn diagnostics on. You have to do this every single time, because when I have you clear your calculator or the calculator gets mem cleared, it doesn't remember your settings. So here's how you do this. First, go second, and then catalog. Catalog is down here, and this gives you a catalog of all the different things you need. So now we want to go to diagnostics. So I'm going to find the D button, which is matrix and X inverse right here. Click that. Arrow down until you get to diagnostic on. Pressed it. Okay, there's diagnostic on, and hit enter. And then you have to hit enter again to actually execute that. It says done. So this tells me that I have turned my diagnostic on. This will give us an R value that we will talk about later. So I'll remind you before we take this test and before we do this homework, but you have to have your diagnostic on to be able to do this. So the first thing is that we need to see if something's linear. That's any time they ask you for something. They said, consider this data. Is it linear? If so, give a line of best fit. So we need to be able to look at data and see if it's linear or not. So here's our first example. Okay. To check to see if it's linear, we're going to go stat edit. Then into list 1, you're going to put your X values. Into list 2, you're going to put your Y values. Then you're going to go to Y equals, turn on plot 1, and make sure to see if the graph is linear or not. So here is our X values and our Y values. Now, the computer in this book decides that you should, instead of putting 1960, we don't necessarily want to put 1960. 1960 is our initial year. That's the 0th year that we're talking about. So if we say that this is going to be X equals 0, well, if X equals 0 is 1960, then 1970 is 10 years later. 1980 is 20 years later. Now, if you don't know this part, you can just subtract. 1990 is 30 years later. 2000 is 40 years later. Now, if you didn't know 2005, again, all you had to do is do 2005 minus 1960. That gives you 45. 2010 would be 50 years later, and then 2014 would be 54 years later. Now, the reason we want to use this as our X value instead of these is just the window. When we look at the window in the calculator, you don't want to have to change your window to 1960 for your X values just to be able to see the graph. You want to just be able to kind of look at it and see it in from 0 to 54. Okay, so this is the deposits and savings account in the United States, actually. So this is actual data. Just kind of as a reminder, this book uses actual real life data from historical records and everything like that. This is in trillions of dollars. So this 0.31, that's $0.31 trillion, or $310 million was in savings accounts in 1960. The last count that they took here was in 2014, and it had 10 trillion. Oh, this isn't even right. This should be 310 billion. I'm off a couple of zeros. Oh, so this is 10 trillion, 133 billion dollars have been in savings accounts. So you can kind of see this inflation as it goes through. So let's see if that, as time goes on, if the amounts in savings accounts increase linearly or if they increase in a non-linear fashion. Well, to do that, we need to be able to plot the points in the calculator. So that's what we're going to do. So to do that, I'm literally just following along here. So to check if linear, we're going to go to stat, which is right here. Stat. Then this is edit. So we're going to hit enter or number 1. Then go ahead and put this data in. Put the 0, 10, 20, 30, 40, 50 into list 1, and then put the deposits in savings accounts into list 2. So I already have them done, but go ahead and pause the video right now and you put these numbers in. All right, hopefully you have this done. All you have to do is type the number and hit enter, type the number and hit enter, type the number and hit enter, and you should be able to have this. Make sure you double check your values that you didn't make a little simple mistake. So now we just finished step 3 here. We put the values in. Now we have to go look at the graph to see if it's linear or not. So you hit y equals, which is up here, top left. Now it says turn on plot 1. If you look at my plot 1 right here, it says it's black. Okay. If yours is not black, it needs to be black. Okay. So you need to arrow up, hit enter, and arrow back down, and it should be black. Okay. So if we look at the graph to decide if it's linear, but normally if I don't know what your window looks like right now, but if you are in normal window, I see 1 point right here, 1 point right here, and that's all I see. Okay, because remember our X values are going from 0 to 54. I only see 0 through 10 in a standard normal window. Well, something else that you can do is to be able to see this, you can go to zoom stat, and it'll go ahead and adjust the window for you. And this is zoom 9, I'm pretty sure. So if I click zoom, which is up here, top middle, this one, and then I want zoom stat. So, if you arrow down or up, you see zoom stat is number 9, and hit enter, and then it automatically does this. So now we're going to see if this is linear. So is this data linear? Well, no, this doesn't look like a line. This more looks like an exponential function, which makes sense because you want your savings to go up over time, right? Deposits and savings. So this is what this data looks like. It looks like, that's the wrong way. It looks like this, right? This is not linear. And since it's not linear, we do not have to give a line of best fit. So when you do my math lab and you do the homework assignments, you'll just choose this data is not linear, and then you're done with it. So let's go ahead and look at the next example here. So we're going to start the same thing. The first X value is going to be X equals 0. From 2010 to 2011 is X equals 1. 2010 to 2012 is X equals 2. X equals 3 and 4 and 5. So our Y value here is the cost of a 30-second Super Bowl commercial in millions of dollars. So in 2010, 30-second Super Bowl commercial cost $2.9 million. This is actual real life data. In 2015, A Super Bowl commercial for 30 seconds costs $4.5 million. It's crazy the amount of money that people have to spend on this kind of stuff, any type of marketing. All right. So the first thing we want to do is, again, see if the data is linear. So here we go. Now what we need to do is to clear a list. This is what we're going to look at now. So, because right now we have this data from the last problem still in our list. So if we go to stat and we go to edit, we need to clear this data out to put the next data in. So you arrow up to list one or whatever list, hit clear and arrow back down. Do not hit delete, otherwise it'll mess your entire thing up. Okay, so hit clear, arrow back down. Oh, I hit vars. So go to stat, edit, hit clear and arrow back down, and then it goes away. So arrow up to the list, hit clear, and then arrow back down, and then it goes away. There's your example. All right. So again, your X values go into list one. So I have 0, enter 1, enter 2, 3, 4. So 0 through 4. And then 2.9, 3.1, 3.5, 3.8, and 4.0. Or just 4. So if you haven't and you're not following along, go ahead and put this into your calculator. Pause it right now and put it in your calculator. Hopefully now you have this in your calculator. So now we need to go look and see if this data is linear or not. Again, if we go to y equals, make sure this plot one is turned on. We're going to try and graph it. So again, right now, this is the same window that we had last time. And it's all bunched up and I can't really see. It just kind of maybe look like a line. But again, if you hit zoom and then arrow down to zoom stat, right there, number 9, hit enter, it'll go ahead and it'll change the window to where you can see it perfectly. Well, if you look at this, these 5 data points are pretty linear. It's not perfect because no real world data is completely and perfectly linear, but you're pretty close here. So it looks something like this, right? Not perfect, but it is linear. So now we will need to write the equation or give a line of best fit. So to give a line of best fit, that's a linear regression. This is probably the part that you remember from Algebra 1. So I'm going to go ahead and second quit out of this. We've turned our diagnostic on, so we'll look at an R value, and we'll talk about the R value later. But once we have decided it's linear, that's this part. Okay, so we are going to go ahead and go stat, calc, linear regression. So stat. Now calc is up here in the middle, so we need to arrow to the right to get to it. And you see lin reg, which is number 4. This is a linear regression. So arrow down to number 4 or hit number 4. We want our X and Y list to be list 1. Make sure your frequency list doesn't have anything in it. If we want to, we can store the regression equation, and I'll show you how to kind of do that later. But let's just go ahead and calculate right now. So this is what you should get now. It tells you that y equals ax plus b. This is what it looks like. Y equals ax plus b, where a is 0.31428, blah, 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 right? And b is 2.84761, blah, 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 blah. All right, to get the linear equation, the line of best fit, that's the linear regression that we just found. So this is it right here. You just have to put it and plug it in. That's it. So A is y equals A is 0.3142857,143. Okay, then you have to have your X, then plus B is 2.84761, 0.9048. All right, there's that. Now it also says, so there's your equation. If they ask for the equation, they'll tell you what to round to. Right here, I'm just writing everything out because we need it for this. It says predict the cost in 2019. So if 2010 is x equals 0, what x value is 2019? Well, 2019, I'm not going to plug in 2019 for x, okay? Because remember, the years are the x values, but it's the years after, number of years after 2010. So 2019 is 9 years after 2010, but all you had to do was subtract, right? In this case, our x value is 9 for 2019. So now all I'm going to do is plug that in. Y equals 0.3142857,143 times 9 plus 2.847619048. Right? All I did was copy that down from right here, plugging in x. So all I did. Okay? So if you actually multiply that out, I'm just going to go ahead and do this for you. Well, I'll go ahead and I'll type it out. So give me a second to type it on the calculator. All right, so I went ahead and typed it on the calculator. Hit it. This gives me 5. So your y value, or the amount in millions, this is 5.67619047. So this is 5,676,190.47, but this extra 7 rounds the 7 up to 48 cents, right? So this is that's how much it would cost in 2019. That's your prediction. Now, I will tell you that the actual cost ranged from 5.1 million to 5.3 million, and this is 5.6 million. So this model that we've made, this linear model, is a little bit high. Okay, they're starting to kind of level off in cost here, but this is a lot of money for 30 seconds. That's how much you're paying for 30 seconds. Now, what I was talking about with the stored, all this blue stuff that I have written up here, you can also figure this out by storing this equation right here in y equals. So if you went to stat, calc, linear regression, right here it says store the regression equation. If we want to, we can say, all right, I want to store my regression equation into y1. So I would go to vars right here, which is right next to the clear button. Vars, I'm going to arrow over to y vars. We want a function and we want y1. So then if we go ahead and calculate, there's my linear regression. Now if I go to y equals here, this is there's your equation. That's the same thing that we just did, right? And if we graph it, there's the line of best fit that goes through the points. Then all you would have to do is you could go to the table and look at x equals 9, arrow down to x equals 9 here. And there's your 5.676, right? So all you got to do is round it just a little bit to whatever you need to. Now let's talk about our correlation coefficient. So correlation coefficient is the R value. Okay, and correlation coefficient tells you how close to a line this data is. So if you have data that looks like this, okay, data that looks like this, there's going to be no correlation here. So this is R equals 0. That means that there is no correlation. It's either 0 or close to 0. So if we have exactly r equal to 1, that is the best thing you can get. So positive slope. Well, r equals positive 1. That means our data fits exactly on a line. If your r value is 1, this is a perfect line, okay? So this tells you that all points are on the line. But if r is really, 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 really close to 1, so like 0.99, okay? So here's maybe a line of best fit through these points. If your r value is 0.99, that tells you that it's a high positive correlation. That means that the closer you are to 1, the better linear fit you get. If you have something that's like maybe super generally positive, but still isn't necessarily aligned, something that looks like this, where the data values are very, very spread apart, your R value will be closer to 0. So maybe even like 0.8 or 0.4, something like that. This is pretty much close to not linear, okay? But it's still a general positive correlation. So this is a low positive correlation. All right. There is not a big difference between these. Basically, the high positives are like 0.99, 0.98, 0.97. When you start getting further away from 0.97, that's not a high positive correlation anymore. That's when you start getting into the low positives. But it'll be very clear when you have it on your homework. Same thing with the negatives. It's literally the same thing. If your R value is -1, that means it's a negative slope. And all points lie exactly on this line. If your points are very tightly knit together, okay, and very linear, that means your R value, again, is close to 1 or -1. So this is -0.99. So your R value is negative because your slope is negative, and this is a high negative correlation. And then same thing, general negatives, but not super linear. This is like r equals -0.8 or -0.4, something like that. This is a low negative correlation. So the key here is that the closer to 1 you are, the better. The closer to 1 you are, the better line the data makes. So if we look at this example with our Super Bowl commercials here, and if I quit out of wherever I am, and I do the stat calc linear regression, just go all the way down, calculate. Here's my R value down here. This is 0.99. This is very, very, very linear. That's another way to kind of tell. And I'll tell you that this R value over here, 0.93. This means that could I make this into a line? Sure, but it's not really a perfect line and it's not the best fit here. This one, R equals 0.99. High positive correlation. This is like super, super, super close to a line, which is what we saw when we graphed it, right? All of these points are very, very, very close to the line. This is what the R value tells you. It tells you how close to the regression the data values are. So how close to the line that the data values are. All right, now that you are done with these notes, go ahead and start on the chapter 1.4 homework. If you need any help, don't hesitate to contact me over Remind or email.